Hi everyone, welcome back to Calculus 2 by Example. In this video we're going to look at ways of approximating functions using polynomials. We're starting with a linear approximation because this is something that you learned in Calculus 1. So this question tells us that we need to find the tangent line to the function f of x equals x plus sine of x at a equals 0. So we want a tangent line right here at the origin. Okay. Remember that the equation for a tangent line is f of a plus f prime of a times x minus a. F of a is because that's the y value, that's the that the function is passing through, and in this case that'll also be the y-intercept. And it's f prime of a because the derivative gives us the slope of the tangent line. Okay, so this is one of the things you probably would have learned early on in Calculus 1. And what we're really going to be doing over the next couple of slides is extending this idea. All right, so because I want to do this at a equals 0, I replace all my a's with 0. And then if I plug 0 into this, I get 0 plus 0, and so that'll just be 0. And the derivative of this function will be 1 plus cosine of x. And when I plug 0 into 1 plus cosine of x, I get a slope of 2. All right. So the tangent line for this function is 2x, okay? So intercept of 0 and a slope of 2, and we can see that very close to x equals 0, very close to the origin, the tangent line gives us a very nice approximation of this function. But as we move further away from 0, the approximation isn't very good. If I'm over here at like negative pi or up here at pi, the approximation isn't any good at all, right? So how can we improve that? Well, this is where something called a Taylor polynomial comes in. And a Taylor polynomial is, in a very real sense, an extension of this idea. It's only, instead of having a linear approximation, we're having this polynomial approximation. This is the general formula, okay? And in general, a term in a Taylor polynomial is the nth derivative. This f to the n stands for the nth derivative, evaluated at a, and that a is called the center of the polynomial. So in this case, I'm still centering this at 0, like I did my tangent line, and I divide by n factorial. And if you've forgotten how this is derived, I encourage you to go back and look at your textbook or look at some of the lecture videos about where Taylor polynomials come from. Today we're just going to focus on using this formula to find the Taylor polynomials for our function x plus sine of x. Okay, so we want f of x equals x plus sine of x. Just to remind you from the last slide, here's a graph of the function, and there's our linear approximation. I left our linear approximation on there. I'm going to find the third degree Taylor polynomial. Again, because I'm doing this at the center a equals 0, I replace all my a's with 0, so it's going to be f of 0, then f prime of 0 times x, then f double prime of 0 over 2 times x squared, and that's technically 2 factorial, but 2 factorial is 2. Then f triple prime, or the third derivative, evaluated at 0, over 6 times x cubed. And it's x cubed because a is 0, so I have x minus 0, and then it's cubed. Okay. So we would need to find the first, second, and third derivatives. The first derivative is 1 plus sine of x. The second derivative, 1 plus cosine of x, I apologize. The second derivative, you should be able to find it on your own, and that's going to be negative sine of x. The third derivative will be negative cosine of x, and then it continues like that. Okay. Plugging 0 into those derivatives, we get that the constant term is 0 and the quadratic term, the squared term, has a coefficient of 0. So we're left with the linear term, which is 2x, and that's what we had found previously with the tangent line. And the cubic coefficient is going to be negative 1/6. Okay? And so if we plot 2x minus 1/6 x cubed, we get this nice cubic. And we can see that the cubic is a better approximation, right? I can go out here to like almost like 3/4 pi or negative 3/4 pi, and I'm still getting a much better approximation than I did with the straight line. It's not a great approximation. It's not a perfect approximation, but it's better, okay? It's still not very good when we get out beyond pi or negative pi. We can continue this process and find the fifth degree polynomial using this same formula. If we do that, we'd find that the coefficient for the fourth degree term is 0, and for the fifth degree term it's 1 over 5 factorial, or 1 over 120. And we can see that that approximation is good almost all the way out to pi. And in fact, visually, if we find the seventh degree polynomial, then the approximation looks really very good almost all the way out to there. Up to this point, just a very little bit less than pi, you can't even tell the difference barely between the function and the approximation, okay? So using these Taylor polynomials, we can get a pretty good approximation of the function using a polynomial, and we want this because polynomials are just easier to deal with. Okay. All right, we're going to finish this video, even though it's a little long, by asking the question, how good is that approximation? So here's our seventh degree approximation, and we can see in the picture that it looks pretty good. But just looking at a picture doesn't really give us an honest estimate of how good it is. So to answer this question, to sort of get a solid number on how good is this approximation, we're going to use Taylor's theorem for error bounds. All right. Taylor's theorem says that the absolute value of the polynomial minus the actual function. So this is the error. This is the difference between our function and the polynomial we're using to approximate the function. That's less than this funny little equation. Okay. The n plus 1 factorial kind of makes sense because it's a polynomial of degree n. And so that's fine. The a is the center for my Taylor polynomial, so that makes sense. M is a tricky one. M is the maximum value of the n plus first derivative. Okay, so if I have the nth polynomial, or the nth degree polynomial, to find out how good the approximation is, I need to look at the next derivative. So here I have the seventh degree polynomial. I need to look at the eighth derivative. Okay, so the eighth derivative is going to be plus or minus sine of x. I don't really care whether it's plus or minus sine of x because I'm looking at the absolute value. And the maximum possible value of sine of x is 1, which means m is 1, which is why I have a 1 here. Okay, and then this value is the absolute value of x minus a. A is 0 because we were centered at 0. And the largest x can be is pi or negative pi. And either way, the absolute value is going to be the same. So that's why that pi is there. So m is 1 because the maximum value for sine is 1. It's 8 factorial because it was the 7th degree polynomial. It's pi to the 8th because I needed an n plus 1 here. And again, this is p sub 7. It's the 7th degree polynomial. And it's pi because that's the largest this value can be. Okay. So if we open up our calculator or Mathematica or a computer and get an approximation for this, this is approximately 0.2353306. So that means that if we use this polynomial to approximate the value of this function on the interval between negative pi and pi, this is the largest the error can be. The largest the error could be is about a little less than a quarter. Okay, and so that gives us a bound on how good or bad the error could be. The actual error will be smaller than that. I want to emphasize this, that this is an upper bound. And if you go back and look at the graph, you should be thinking, well, Dr. Rocca, that error looks a lot less than a quarter. And you're right, the error is a lot less than a quarter. That's because this gives us an upper bound, but it doesn't give us a least upper bound. It doesn't give us an exact value for the error. It's just giving us a nice approximation. Okay, so that's it for linear approximations and Taylor polynomials and their errors. What we're going to do now is I'm going to take a little break, and I'm going to come back and do one more short video where I talk about Taylor polynomial or Taylor series, which is what happens when we just take a Taylor polynomial and just keep going. So I'll see you in just a minute for that.